Hello students, this lecture is about modes of heat transfer. So we have learned in previous lectures that heat is the transfer of thermal energy from one object to another. And we're going to learn about how that happens. There are three main ways that heat can happen, and we'll take a look at what makes each one work. So that's our first objective, to be able to identify the three heat transfer modes based on how thermal energy is moving. We're going to take a brief look at something called Fourier's law of conduction, and we'll see what implication that has for how heat is conducted. And by the end of the lecture, we should also be able to list examples of the three heat transfer modes and be able to justify why those are good examples of each. Let's start with some notes about the different heat transfer modes. The first one we're going to talk about is called conduction. And conduction is heat transfer through a solid object, which is an important part of the definition, or between solid objects that are directly touching. So something that's solid or directly touching something else is going to be transferring thermal energy through conduction. Thermal energy can also move through the vibration of molecules. And what we mean by that is, let's say I have molecules. If we zoom way in on a solid object, I would have molecules that make up that solid object. And let's say one side of this solid object has a higher temperature than the other side. Those are my red dots over there. These hotter molecules are going to be vibrating more because they're at a higher temperature. We know that from previous lectures. So as they vibrate, they're going to bump these other ones next to them and then move the heat down a little bit more, or excuse me, move the thermal energy down a little bit more, because now these molecules on the right are moving faster. They're going to bump the next one, bump the next one, bump this one, bump this one, and you can see that the higher temperature moves from hot to cold all the way down through the solid object. So within an object, these molecules, we can consider them as bumping into each other and transferring thermal energy, and that's also conduction. There is a law called Fourier's law of heat conduction, and it states that the rate of conduction, so how fast conduction happens, this word rate means how fast. How fast conduction happens. And that is going to be directly proportional to a couple of things. One, the temperature difference between the two objects. So if I make the difference between the temperatures of two objects greater, heat conduction is going to happen faster. And we'll see a graph of that in a moment, and also we'll see some examples of that in class. Our conduction also depends on the surface area of the objects that are in thermal contact. If I have a very small surface area touching between the two objects, then not much heat flow is going to happen. But if the two objects are in a lot of contact, there's a lot of touching between the objects, then more conduction can happen. There can be more heat flow. We could see this on a graph of temperature of two objects. Let's make this temperature in degrees Celsius and time in seconds. If I take two objects and I put them close to each other, we have seen the way they reach thermal equilibrium is I can take a hot object and it's going to eventually come to some temperature and level off. And the cold object, if I have them touching, is going to gradually come up to that same temperature. So here we have cold object, and up here is the hot object. We've already seen in our investigations that heat occurs between both of these objects, and thermal energy is going to flow from hot to cold until they eventually reach the same temperature. And we called that thermal equilibrium, in a previous lecture where they reach the same temperature. Notice right here, conduction is happening very quickly. There's fast change in temperature because the difference in the temperatures is very high. Notice when we get right over here, let's say over here, the temperature isn't changing very quickly at all. It starts to slow down a lot more because now the temperature difference is very small. So we'll call this fast change, and over here, let's call it slow change. Okay, this is the main implication of Fourier's law of conduction, is that when the temperatures of the two objects are very different, then they're going to change their temperature very quickly. And when the temperatures of the two objects are not so different, then the change is going to be much slower. And of course, when we finally reach thermal equilibrium, the temperatures are not going to be changing at all, because now they're at the same temperature, all nice and balanced out. So let's go to the second mode of heat transfer. Remember, there are three ways that thermal energy can move. Conduction is one of them, and the second way is called convection. And we're going to define convection as heat transfer through the motion of a fluid. And by fluid, I mean anything that's not a solid. So a liquid, a gas, or a plasma. If the fluid itself is actually carrying thermal energy from one place to another, we call it convection. So thermal energy carried by a moving fluid to a new location. This is different from conduction, because remember, conduction, we're mainly concerned with solid objects, and those objects need to be touching each other directly. Convection, we're actually moving something like air or water from place to place, and that can move thermal energy with it, which is kind of cool. So there's going to be two different kinds of convection. One is called natural convection, and this is maybe something you learned about in middle school. Natural convection occurs naturally. This is something that just normally happens out in nature and in the world. So a fluid at a higher temperature is going to have a lower density, and it's going to tend to rise. So this is something you may have heard as hot air rises, for example, or hot water rises. And that's where this comes from, is a principle of natural convection. The converse is also true. So if the fluid is at a lower temperature, it's going to tend to fall. It wants to go down lower. And we'll see an example of natural convection in an image that I have for you. If we take a look at this room, we have an object called a radiator over here in New England. We have a lot of these, radiator. And it actually doesn't radiate heat too much. What it's doing more of is actually convecting heat to make the room warmer. There's going to be air that comes in here, gets very warm by touching the radiator. It's going to rise and flow around the room because it's pushing colder air out of the way. The colder air comes back around from the ground and goes back to the radiator. We have this circular motion of air convecting throughout the room. That is called natural convection. So what nature is always trying to do is create thermal equilibrium. We know this from previous lectures. So what the fluid is actually doing is circulating so that it can try and even out the temperature in the room and try to make everything all the same temperature. Okay, because this is the ultimate goal. Thermal equilibrium means we want everything to get to the same temperature. There is another kind of convection called forced convection. And this is pretty much exactly what it sounds like, which is we are forcing air or water or some other fluid to move. How do we force a fluid to move? We do it with a pump or a fan. These are some of the most common ways of cooling rooms or cooling devices is to use a fan. and we use the fan to make air move and flow across an object that needs heating or cooling. And this is a very efficient mode of heat transfer. It occurs very quickly. So when your coffee is too hot, what do? You blow on it. And that is forced convection. You are forcing air to move across the surface of your hot coffee, take some of the thermal energy away, and therefore your coffee is going to drop in temperature because you're removing thermal energy. That is an example of forced convection. And it's pretty efficient, which is why we use fans for cooling everything from computers to rooms. If you want to get your hair very hot to evaporate some water out of it, we use a hair dryer, which is forced convection. So we see these applications everywhere. So air conditioning would be an example, fans, vents, hair dryers, heater, engine cooling. Depending on the car engine, you might have forced convection, where there's a fan in the front of the car that's pulling relatively cool air from outside over the radiator of the car and taking away the engine's thermal energy so it doesn't get too hot. You may have noticed computers such as laptops and desktop computers have a little fan in them to cool off the processor. So what's common about all these is that there's some kind of pump or fan that is moving a fluid so that we can take thermal energy from one place to another. That is forced convection. Let's take a look at the last form of heat transfer, which is called radiation. And radiation is heat transfer through electromagnetic waves. We have not studied electromagnetic waves yet. We will in a later unit. But for now, we can think of electromagnetic waves as light, microwaves, infrared waves, X-rays, basically anything that normally moves invisibly through the air or through nothingness at all, that we can't see, but we know there's energy moving from place to place. We can call that radiation. And what's happening is that thermal energy is going to travel through the electromagnetic field until it gets absorbed by matter. Matter means something with atoms. So something with atoms. An example would be light energy from the sun is traveling by radiation to us. When it reaches us, it hits matter, which is the Earth or us standing out in the sun, and it turns into thermal energy or heat. It's going to make us hot. Something special about radiation is that it is the only mode of heat transfer that can travel through a vacuum. Both conduction and convection require atoms or molecules to be present so that they can work. In conduction, molecules have to directly touch each other and hit each other to transfer thermal energy. In convection, those molecules have to physically move as a fluid from place to place to carry the thermal energy. In radiation, no atoms required. So, when we talk about a vacuum, we really mean empty space. So how does thermal energy get from the sun to us? It has to travel through light. It has to travel through empty space using radiation. Let's take a look at my other examples of heat transfer. So in the first case, I have a cold spoon that has been placed into some hot chocolate, and we have thermal energy moving from the warmer object, which is the hot cocoa, through the colder object, because remember, anything that's in thermal contact wants to come to the same temperature. So we need to increase the temperature of the spoon. How does thermal energy get from the hot cocoa to the spoon? Well, it actually flows through a solid object to get distributed through the spoon. This is an example of conduction. because thermal energy is moving through a solid object to get distributed from one place to another. We talked about this one. This is a case of natural convection, where warm air is naturally rising to the top of a room, thereby pushing the cold air down and back towards the source of heating. And we're going to get this circular motion inside of a fluid, such as air or water, that redistributes the thermal energy. And it once again tries to make everything come to thermal equilibrium. These are examples of forced convection. On the left here, this is actually called a convection oven. And it's not by mistake it's called a convection oven. It actually uses convection to heat your food. If you notice in the back of a convection oven, there is actually a fan at the back. And so we make the convection oven very hot, or a heating element very hot, and the fan is going to force air to move around inside of the convection oven. And that hot air is going to move thermal energy to your food, which is what you want to get cooked. And convection ovens are nice because you have moving air that is going to move the thermal energy all around and kind of evenly distribute the thermal energy, so your food gets cooked very evenly and from all sides. On the right hand side over here, this is a hair dryer, of course, and it's another example of forced convection. There is a fan inside of the hair dryer and some heating elements. There's some coils that get very, very hot, and we're going to take in cool air from this side, and we are going to blow out hot air from the other side. This is an example of forced convection, because we are taking thermal energy from inside the fan. Of course, we're not creating thermal energy. Electrical energy has to come in. And we turn that electrical energy, we convert it to thermal energy, and then we send it out of the hairdryer in the form of forced convection, so we can distribute it to something else, presumably your hair. Here are some examples of radiation. Remember that radiation does not require matter to move thermal energy from one place to another. So a good example is the sun. Thermal energy is radiating outward through space from the sun, traveling by electromagnetic waves, such as light. And we can say light or electromagnetic waves. And we also see radiation happen even here on Earth. If you are holding your hands next to a fire, you're going to feel thermal energy from that fire through radiation from the side of the fire, or a flame. Of course, right above the flame, there is hot air rising. If you were to place your hand above a fire, be careful, you would feel some very hot air moving in a column straight upward. That is actually convection, because hot air is carrying thermal energy upward. So if we're above a flame, it's convection. If we're on the side of a flame, we're actually feeling the thermal energy transfer through radiation. So let's go back to our objectives for modes of heat transfer. You should be able to identify the three heat transfer modes, conduction, convection, and radiation, based on how thermal energy is moving. So if it's going through direct contact or through a solid object, we're talking about conduction. If it's going through a moving fluid, we are talking about convection. And if it's happening through electromagnetic waves, such as light or microwaves, then we are talking about radiation. Objective number 2, you should now be able to understand the main implication of Fourier's law of conduction. That's when we were talking about how quickly conduction happens based on the temperature difference between two objects. And finally, you should be able to list examples of the three heat transfer modes with justification. Think about examples in everyday life where we are moving thermal energy from one place to another, and see if you can justify whether or not those things are conduction, convection, or radiation. We're going to discuss in class next time we meet.